this works. Okay, so I hope you can hear me. So let's talk machine learning in space. So this is the second presentation that I do in the doctoral meetings. So I'm very happy to present many updates compared to the last year. The main topic of the research is the application of deep learning techniques for optical navigation. So for different use cases in the solar system exploration missions. So as a very brief introduction, the main idea is to study applicability of using convolutional neural network or even other type of neural networks for optical relative navigation to substitute the traditional feature-based algorithms, which are maybe not so robust in some illumination conditions and also very resource-consuming. So the idea is to instead train a neural network to directly learn the nonlinear transformation between the 2D space of a grayscale image or 3D for a colored image. 2D space have pose vectors, so 6D space, so 3 coordinates for the position vector and 3 Euler angles for the attitude. So yeah, the idea would be something like this. And the use case is like this, right? So we are in the case of a minor body. So we have the camera with the fixed frame of the camera orbiting an asteroid with its body fixed frame. So we want to estimate the vector R and the rotation matrix or Euler angles to transform from the frame of the asteroid to the frame of the camera. But of course, there are some challenges that we have to address as in almost any neural network or machine learning problem. The main one is that normally the neural network acts sort of like a black box. So we kind of tune it, but we don't really know what's happening inside. So we have to perform extensive testing to validate all the use cases and identify any possible failure cases before going to operations. Also, as it's very well known, machine learning requires a lot of data. And for these kind of cases of space missions, even though we have very large archives like for Rosetta, OSIRIS-REx, Hayabusa, but still it's not enough to train for a general solution directly using the images from these archives. So we need to extend this data that we use for training. And then, of course, we want to generalize the machine learning solution because we want the neural network to work for as many use cases as possible. So for many ranges of positions, illumination conditions, perturbations like dust, things like this. So these are the main 3 challenges that we have to address. And to do it, we do 2 main tasks. So the first one is because we don't have enough data to train, we generate more data. And we do that by rendering synthetic images, which are very realistic and implement many of the effects which come from the real images. And we do so with a package that we developed in the last years called SpyRender, which is fully Python-based, and it uses GPU-accelerated graphics. So it's very fast, and we can generate data sets with tens of thousands of images very quickly. So it's very useful for rendering these kind of images, which, as you will see, are very similar to the real ones, and that we have actually used to successfully train the networks. And compared to one of the latest features that we added in this package is that the shape model and the texture of the target, which we found it's really important to fill the gap between synthetic and real images, can now be modified during runtime. So in runtime, we can apply data augmentation to the shape, modifying the small scale features of the shape, also the texture of the shape models. And then when we have all this data that we generate, we of course need to design and train the neural networks that will finally estimate the position. So we started with a very simple architecture based on AlexNet, just to study the different effects, the impact of different geometric effects on the performance of the network. And then we moved to more interesting architectures like very deep neural networks and efficient-oriented architectures and check the performance using those. And in addition, it was very important to configure properly the training. So this was to define a custom loss function, define the different layers, use classification or use regression for estimating the position, also the data augmentation techniques. So these are the main 2 activities that we are doing to solve the problem. So for data augmentation, which is really important, and here on the right shows a brief example of the same image, but for which different data augmentation effects have been applied. So of course, we want to generalize the machine learning solution. So we applied different data augmentation. Well, maybe some of them are not strictly data augmentation, like we generate images for the whole range of positions, so longitude, latitude, and altitude. Of course, the whole range of roll angles, so the angle around the bore sides of the camera, and pitch and yaw angles, which is almost equivalent to the shift of the target with respect to the center of the image if you start from a near point in frame. But then on that augmentation, what we really do is to apply random illumination conditions, so random direction of the illumination source and random intensity to produce overexposed and underexposed images. Also Gaussian noise to model the noise of the images, but also other effects like dust ejected from the comet in the case of Churyumov-Gerasimenko, or if you have seen the very nice images from DART, the whole bunch of dust that was ejected after the impact. So these kind of things. And then we wanted to include also these two, which are not very common, but it's basically field of view invariance. So we want the network to work with images which have been captured with different cameras. So for example, for the case of Osiris Rex, it has cameras with 20 degrees field of view, 5 degrees, and less than 1 degree, I think. So if you take images with a very narrow field of view when you are very far from the asteroid and you perform a model, and you use that model for training, then you want the network to also work when you are very close to the asteroid with a wider field of view, which, well, there will be some optical distortion, but still you need to work. So by using different field of views in the training set, we achieve this thing that we call field of view invariance. And for the spatial resolution invariance, it stands for variations in the shape model. So you want the network to work with real images, but maybe you don't have such a high detail model. So by using also different shape models in which you have modified a bit the low scale features, you make the network to rely on the big scale features, which maybe do not change much. And then in this case, you achieve this kind of invariance. And also it's very important not only to apply this data augmentation, but the way in which we applied it. And it has to be always during runtime. And this is because if we have a training set, let's say 40,000 images, if we apply data augmentation before training, those images will be the same and the network will overfit and it will not find a general solution. So for every epoch of training, we need to apply the effects again. In this case, the data set, instead of 40,000 images, if we have 100 epochs, is 40,000 times 100. And this really affects the performance in the general solution. So this is just an example of the real images at the bottom and the synthetic ones at the top for the case of Bennu asteroid. So these are images from the MapCam camera of the Osiris Rex mission. And the model, it's at, I think, 1 meter spatial resolution with the albedo map, which is captured by images from the Polycam at very low phase angles. So we found that it's really important not only to use the same models, maybe in other targets which doesn't have too much albedo variation, it's okay. But in the case of Bennu, you can see maybe some small rocks which are very white, obscure areas which are darker than other parts. And you can see the same thing in the real images. So this is why it's also very important to account for albedo variations when we want to fill the gap between synthetic and real images, which is in the end, it's the real goal of the investigation. So for the neural network, as I said, we started with a very simple one, so just 2 convolution layers, 2 fully connected layers, because it's much easier to train, it's much faster, and then we can evaluate the impact of the different effects of the data augmentation effects that I saw before. But then once we know more or less the trends and the impacts of these effects, and we know for which conditions we want to train, we can go to more interesting networks, which indeed, as you will see, really improve the accuracy. And just to mention in comparison, BGG comes with 19 convolutional layers compared to the 2 that we are using in the base model. So that's why we get much better accuracy. This was presented already, and we have kept this approach because it really works. So the problem with using classification or regression is that for regression, we cannot estimate a global position because there are simply very large gradients because of the nonlinearities to transform from the image to the position. And for classification, of course, accuracy depends on the level of discretization of the space. So what we use is a hybrid approach. So we have first a classification which estimates the sector of the 3D space in which the image was captured. And then based on that classification, we have a set of low-level regression neural networks. Each of them is trained only for one sector of the 3D space. So we have 32 sectors, 32 regression neural networks, which indeed estimate the position accurately. And in addition, we add a high-level, what we call high-level regression, CNN, which basically centers the target in the image, even when some part of the target, and actually a lot of the part of the target is outside of the field of view, it centers it in the image. And that's simply because we found that that boosted performance of the consecutive networks, well, by more than 20% in classification, and by, also something like 20 or 30% in the loss for the position regression. So that's more or less of the approach. So for classification, we already have something that works, but we really wanted to try something different, which in this case was the time-distributed neural networks. And the main difference compared to the traditional ones is that instead of using a single image as input to the network, we use a sequence of frames. So in this way, we take advantage of the dynamics of the use case. So in this case, the spacecraft orbiting the asteroid. So basically, we have a CNN, which we applied the same coefficients and the same architecture of the CNN to each frame of the sequence. 4 or 5 images apparently works fine. And then we introduced the output of each of these CNN to a time-distributed ledger like the GRU, which combines this input and then goes to a decision network, and then we have the sector estimation. And here on the plot on the right just shows the best case that we have for the single CNN, for which we had an accuracy of about 40% compared to the time-distributed ledger with the same convolutional neural network that we applied for the single CNN. And we have a boost in accuracy of more than 20%. So this shows that really we have something here to keep exploring, and maybe to even try to estimate directly from the neural network dynamic quantities like angular velocities or linear velocities of the spacecraft. So something that indeed we want to explore further. Then for the low-level regression, so we are normalizing the output such that the x, y, z coordinates of the position vector goes from 0 to 1. And then we use a custom loss function. So instead of the mean absolute error, mean square error, which are typically used in these cases, we use a translation error to minimize during training. And also we found it's very important to have a proper schedule of the learning rate. So adjust the learning rate as we go further in the training epochs. And you can see the importance here. So apparently, we were going to achieve convergence at 150 epochs, but then we decreased a bit further and we really improved the loss something more. So it's also something to take into account, the schedule of the learning rate during training. So as a summary for the low-level regression, so we have tried all the geometric effects that I mentioned with the dot augmentation, but also some more, like the spatial resolution, and also the pixel resolution of the image that we ingest to the network. And as a very brief summary, I will just focus in the plot of the right. So you can see that going from the low-level model, which is the blue bars, to the high model, the high-resolution model, the loss function really goes to more than half. And this is simply because we have more features which the network can use to basically estimate the position. Similar thing, if we go from 224, which is the standard image resolution, to 480, again, we have a big boost in the accuracy, and we reduce a lot the loss function. And then when we went with the same conditions to a more interesting architecture like the BGG19, which is the orange bar here, the accuracy, the loss function reduced again half of it. And in this case, we are already achieving accuracy as good as feature-based methods, but more robust as it works also in adverse illumination conditions. So, and this is the main goal of the current stage of the investigation, which is that it works with real images, which is that something that hasn't been achieved before. So basically, we scale the images from OSIRIS-REx to the 224 or 480. We center the target in the image because some of these images are, of course, generally it's not fully nadir. So we center them, we provide them to the high-level classification, which redirects the image to one of the low-level regression networks, and it estimates the position vector, which, as you can see, for almost 20-kilometer altitude, it has accuracy on normally 100 to 100 meters of loss. So something that we have tested also in a Kalman filter investigation by Thomas, and it works nicely. So this is a big milestone for us. So very quickly on the achievements, so we'll present these results in the GNC conference from ESA in a couple of weeks in Poland. Also, we had a journal paper accepted in the Transactions in Space and Electronics journals from IEEE on the previous investigation of TuringNet, but we will prepare a paper for the these, the latest developments and, the results with the real images from OSIRIS-REx. And also we have an abstract accepted in the IAC in Baku, in which we'll present the results for CAMNET, which is the similar investigation that we do, but for the Earth observation case. And last, about some work to be done in the next year. So we want to, now that we have achieved to fill the gap between synthetic and real images for the case of the asteroid and comet, we want to do the same thing for the Earth case, which it's probably the most difficult one because of the seasonal variations. Something which is green in March is completely yellow in July or white in December. So it's much more challenging. Also, you have clouds and many different things. Also, to extend the usage of time-distributed neural networks. So we want to use it also for regression, to compute velocity, for instance. And also, we want to investigate the applicability of this approach to other targets. So one which is very interesting is Phobos and Deimos, given that the Martian Moon Explorer mission will arrive there in less than 2 or 3 years, I think. And we have very good models of these 2 moons of Mars from Viking, from Mars Express. Also for lunar orbit and in the end Mars and Mercury. And also if you have any other suggestion, we are open to. So thank you for your attention.
Okay, thank you.